The trajectory of any spacecraft always consists of active and passive propulsion phases. Inside the calculated sphere of influence of a planet, its gravitational impact is considered primary for the spacecraft. The minimum third cosmic velocity allows a launched object to permanently leave our solar system. A successful gravity assist maneuver allows efficiently accelerating interplanetary probes absolutely without any fuel consumption.
Welcome. Today, we're going to conduct a rigorous examination of the fundamental principles governing the movement of spacecraft. You see, sending a probe to another planet isn't simply a matter of brute force. It's an intricate dance with the laws of physics, a discipline we call celestial mechanics. Let's delve into the core concepts that make these incredible journeys possible.
Our lecture today is structured into 5 core sections. We'll begin with the basic phases of any spaceflight. Then, we'll define the crucial concept of the sphere of influence. From there, we'll quantify the speeds required to break free, the cosmic velocities, and explore the elegant technique of the gravitational maneuver. And finally, we will examine how these principles were put into practice by the pioneers of deep space.
All right, let's begin. Every single spacecraft trajectory, without exception, is composed of 2 fundamentally distinct phases. You can think of it as 2 separate regimes of flight. One where we are actively in control, and one where we surrender control to the universe itself.
So we define the trajectory as this entire path. It's a carefully calculated sequence of powered or active segments and unpowered or passive segments. This distinction is absolutely critical because rocket fuel is an extremely limited resource. The vast majority of any interplanetary journey is spent coasting. And this illustrates the 2 states perfectly. In the active section, the engines are firing. Motion is determined by that thrust, fighting against gravity. But the moment those engines cut off, the spacecraft enters the passive section. Its motion is now dictated purely by the gravitational forces of all the celestial bodies around it. The Earth, the Sun, the Moon, Jupiter. It becomes a creature of gravity.
So that leads to a complex problem. If multiple bodies are pulling on a spacecraft, how do we calculate its path? This is the classic in-body problem, and it's notoriously difficult to solve. To make things manageable, we have to define which gravitational body is in command at any given time.
We do this using the concept of a sphere of action, or more commonly, the sphere of influence. Essentially, it's a way to simplify the physics. We draw an imaginary boundary around a planet. Inside this sphere, we treat the planet's gravity as the only significant force. Outside of it, we consider the sun's gravity to be dominant.
This diagram is an excellent visualization. You can picture space-time as a fabric. The sun, being massive, creates a very deep gravity well. Earth creates a much smaller well that moves along with it. The formula you see here allows us to calculate the precise radius of Earth's local well, the boundary where its gravitational pull becomes stronger than the sun's tidal or disturbing force. For the Earth-Sun system, that sphere of influence extends approximately 930,000 kilometers from the center of the Earth. To put that in perspective, that's almost 2.5 times the distance to our own moon. Any spacecraft within this region is primarily an Earth satellite.
Now, by comparison, the moon's sphere of influence relative to the Earth is a much smaller 66,000 kilometers. This was the precise gravitational boundary that the Apollo missions had to cross to transition from being governed by Earth's gravity to being captured by the moon's.
Having defined these gravitational domains, we can now quantify the energy, which we express as velocity, required to transition between them. These are not arbitrary numbers. They are fundamental speed limits baked into the structure of our solar system.
The first critical threshold is the second cosmic velocity. You probably know it by a more common name, escape velocity. This is the minimum speed an object needs to achieve to break free from a celestial body's gravitational pull permanently.
This diagram shows it beautifully. At lower speeds, your trajectory is a closed ellipse, an orbit, or you simply fall back to Earth. But as you increase your speed, that ellipse stretches out. At precisely 11.2 kilometers per second near the Earth's surface, the orbit stretches to infinity. The path becomes a parabola, and the spacecraft will never return. It has escaped.
But escaping Earth is just the first step. To leave our solar system and travel into interstellar space, a spacecraft must escape the gravity of the sun itself. This requires a far greater speed, the third cosmic velocity.
Now, the calculation for this is fascinating. From Earth's orbit, the solar escape velocity is 42.1 kilometers per second. But we get a tremendous advantage. The Earth itself is already moving at 29.8 kilometers per second, So we leverage that motion. We only need to provide the additional velocity on top of that, plus enough to climb out of Earth's gravity well. It's like jumping from an already fast-moving platform.
And this makes the launch direction paramount. If you launch with Earth's orbital motion, you only need an initial velocity of 16.6 kilometers per second relative to Earth. But if you were to launch against that motion, you would first have to cancel out Earth's 30 kilometer per second speed and then build up the necessary 42 kilometers per second from there. The required launch speed would be a staggering 72.8 kilometers per second, well beyond our current capabilities.
Now we arrive at one of the most elegant and powerful techniques in all of celestial mechanics, a method for gaining enormous amounts of velocity without expending a single drop of fuel, the gravitational maneuver.
You've likely heard this called a gravity assist or a slingshot. By precisely navigating a spacecraft into the gravitational field of a moving planet, we can intentionally alter its trajectory and velocity relative to the Sun. This technique literally unlocked the outer solar system for exploration.
Here is how it works. As the spacecraft approaches the planet's gravity pulls it in, bending its path. The key is that the planet itself is moving rapidly in its orbit. The spacecraft effectively steals a minuscule amount of the planet's vast orbital momentum. So while its speed relative to the planet remains the same as it leaves, its speed relative to the Sun has been significantly increased.
Now, these principles are not merely theoretical exercises. They have been the foundation for some of humanity's greatest voyages of discovery. Let's look at key historical milestones where these very concepts were put to the test.
In 1959, the Soviet Union's Luna 1 became the first human-made object to achieve the second cosmic velocity, escaping Earth to enter an orbit around the Sun. Then, in 1972, Pioneer 10 masterfully executed a gravitational maneuver around Jupiter. That flyby gave it the velocity it needed to achieve the third cosmic velocity and become the first spacecraft ever placed on a trajectory to leave our solar system.
So, we have seen how a deep understanding of gravity, trajectories, and velocities allows us to navigate the solar system. The mastery of these celestial laws has taken us to the farthest reaches of our planetary system and even set us on the path to the stars. This concludes our analysis, leaving us with the final thought. Now that we understand the rules of the cosmos, where shall we endeavor to go next?
Thank you, friends. Strive for understanding and become wiser. See you soon.